Welcome to ISE 330. I'm your instructor, John Gunnar Carlson. I'm looking forward to teaching this way. It's a new experience for me, and I hope I do an okay job. The reading for the lecture today is up here. It's optional. These are all from the free textbooks that you've seen in the syllabus. You're welcome to read it if you like. You don't have to. That's just for your enrichment. Let's get right to the start here. What are deterministic models? The word deterministic just means not random. So a deterministic model is a mathematical model like an equation or an algorithm or a theorem that you use to solve a real-life problem in which all of the inputs are known with certainty. So there's nothing unknown about the problem. There's no probabilities. There's no random variables. There's no Bayes' theorem. There's no expectation. There's no variance. Examples of deterministic models would include Newton's laws, F equals ma, an object at rest tends to stay at rest, these kinds of statements. There's nothing random there. The Navier-Stokes equations, which you probably haven't seen, they're partial differential equations that describe the movement of a fluid. Again, there's nothing random in them. Supply and demand curves from economics typically don't have randomness attached to them. You distinguish deterministic models by comparison with stochastic models. That's the opposite of deterministic. The word stochastic just means random. A stochastic model is a mathematical formulation, like an equation, algorithm, or theorem, that you use to solve a real-life problem in which the outputs are not known exactly. There's some randomness involved. Okay, so anything with random variables is stochastic. It just means random. Weather forecasting would be an example of that. You say there's a 90% probability of rain tomorrow. Most quality control models are stochastic because you have to deal with the random chance of a component breaking or of a machine failing, something like that. The Black-Scholes formula, you probably haven't seen this. It's an important formula in mathematical finance. It's an example of what is called a stochastic differential equation. It has nothing to do with this course. We're not going to touch any of this stochastic stuff. For that, you go to ISE 331. So what are mathematical models for? Either deterministic or stochastic. It's important to understand what we mean when we talk about mathematical modeling. Okay, one thing you might want to do is explain a phenomenon. Right, there's something you observe, and we're industrial engineers, so we care about industry, so we care about making money and building things, among other processes. You'd see a CVS that's built right next to a Walgreens, right, or a Burger King right next to a McDonald's. Or you're driving along an empty highway and you suddenly see a cluster of gas stations all right next to each other, right? So an economist or an industrial engineer would say, what's going on here, right? Why do they tend to clump together like this? You could go and ask the person that built the store or built the gas station. You might get an answer there, but you might want to formulate some kind of mathematical equation or mathematical formulation that answers this. Harold Hotelling did this in the early 1900s. He formulated what's called Hotelling's law, which is a mathematical rule that explains why this is likely to happen. You might want to make predictions, right? I might want to know, okay, what do I think the future is going to be like? You might want to ask how long it's going to take you to drive to work tomorrow. Right? Then you'd fire up Google Maps. There's a whole lot of complicated math that goes under that. You'd have to find what the shortest path is. You'd have to estimate how long you think things are going to be. That would probably be a stochastic model because you're predicting something that you don't know about. You might want to do decision support. You might want to decide what's the best decision for me to make. Maybe I have a bunch of customers that I have to visit by driving a van to repair their electrical meters or something like that. And I'd like the shortest route that visits all of them. I'd say, what's the shortest route I can take, right? What is the right sequence that I should visit these customers in? That is like the quintessential operations research optimization problem called the traveling salesman problem. If you're Starbucks and you're releasing a new kind of latte and you want to know whether you should sell it for $4.50 or $4.75, that would be a decision support question. You're asking, how do I decide what the best decision is that I need to make? And typically you're using a lot of math to do that. Sometimes a model is useful just because of what it communicates. You come up with a mathematical principle that is easy to articulate to your customers or your supervisors or your students. The 80-20 rule is a great example of this. 80% of your sales come from 20% of your clients. That's called the 80-20 rule. It's also called the Pareto principle. It's named after Vilfredo Pareto, who was an economist in the turn of the century. 1896, I think, is when he wrote the paper about this. It's a general principle that applies in a lot of contexts, that 80% of the effects are due to 20% of the causes. It's not just a catchy statement. There's actually some deep mathematics behind it. And Pareto was an economist who identified this. There are two sides of what you're going to learn in this course. There's two sides that are both important. The first is mathematical modeling. Okay, mathematical modeling means your client comes into your office and tells you their problem. They tell it to you in words. They're probably not mathematicians. They're probably not engineers. They say, I'm trying to make money. I have this kind of process that's in place. Here's what I've got under my control. Here's the outside forces I can't control. Help me solve this. You as an engineer then take all those words that you've heard, and you turn those into a mathematical model. You convert that into a mathematical expression. You say, well, you have a utility function that we can model as, x squared minus 9x plus whatever it is, and we're going to minimize that, and we're going to differentiate it and set the derivative to 0, and then we're going to come out with a solution. That's the model. Now, the actual question of solving these models is also hard. And that's what we call optimization, which is what we're going to learn in this course, mathematical optimization techniques. There are 3 of these. You don't need to know what these mean yet. Linear programming, integer programming, and dynamic programming are 3 families of algorithms that you're going to learn in this course for solving mathematical optimization problems. Let's next talk a little bit about some history of deterministic models. In 350 BC, this is the earliest example of a deterministic model in industry that I could think of. Aristotle had a family of books called Nicomachean Ethics. He talked about justice and distribution and exchange of scarce resources. Okay, and there are some mathematical models that went in there. The ancient Greeks liked to talk about things in terms of geometry. And in this case, he was talking about proportion when he was talking about how you should decide the right price to buy or sell something. He said, in any kind of action in which there's a more and there's a less, there's also what is equal. The just then must be both intermediate and equal and relative, i.e. for certain persons. Okay, what is going on here? Here's a simple example from this, which I've paraphrased. You've got 2 people here, and they're arguing over how much something is worth, right? The buyer wants to buy the item for $50, and the seller wants to sell it for $100. And so Aristotle said, well, let's try and figure out mathematically what is the right price that we should go for here. The most natural thing to do is arithmetic proportionality. Split the difference, right? If the low ball is 50, the high ball is 100, well, split the difference, that's $75. Okay, that's arithmetic proportionality. That's the first bullet that you see there. The second is geometric proportionality, which means that the ratio of the price to the party's desired price should be the same. I've got this formula here that says P over A is equal to B over P. And therefore P is equal to square root of AB. I'm not going to talk more about these in examples because that's going to be on the problem set. These are 3 rules by which someone could construct a quote-unquote fair price for an item. And one of your assignments on the problem set is going to be to kind of explain these in words. Around 1300, Ibn Taymiyyah was a scholar who talked about the laws of supply and demand. This is the earliest reference I can find to this. It had been understood, or it had been sort of assumed that prices going up and down were due to people being unscrupulous or dishonest. Ibn Taymiyyah was one of the first sort of economists who recognized that, well, maybe this is actually just a natural part of how markets work. He said, rise and fall in prices is not always due to injustice of some people. Sometimes its reason is deficiency in production or decline in import of the goods in demand. Thus, if the desires for the good increase while its availability decreases, its price rises. On the other hand, if availability of the good increases and the desires for it decrease, the price declines. The scarcity and abundance may not be caused by the action of any people. It may be due to cause not involving injustice, or sometimes it may involve injustice. So he's giving himself an out there. 1854 was the famous cholera outbreak that was an early application of what are called Voronoi diagrams that we'll look at in a minute. The Soho district of London in 1854 had a severe outbreak of cholera. And most doctors at the time believed that cholera epidemics were the result of things like disease, filth, environmental conditions. It's too hot, it's too humid. Right? The germ theory of disease, I guess, wasn't fully accepted at that time. John Snow was a physician who postulated that actually it was due to germs. And he expressed this using a diagram that I'm going to show you on the next page that illustrated or demonstrated why it was likely that, in fact, cholera was being spread due to germs. In fact, he found the picture that you see here. So this is a map of the Soho district in London, okay? And you'll see it's colored by a lot of things. So what is going on here? When each of these colored cells, you'll see there's a little blue dot. Each colored cell has exactly one blue dot inside it. Each blue dot is a water pump where people would go and get their water. And so these cells, these colored pieces here, correspond to the regions where that pump is the closest one to you. So anyone in this, if you look down there, this is kind of a lime green cell there. That lime green cell, everyone preferred this pump here at the lower left. And he said, look, if you look at where the cholera cases happen, which is these red dots here, they all tend to be clustered around this yellow pump in the middle, or the yellow cell there, which corresponds to this pump in the middle. And he said, look, what does that tell us? That tells us that the cholera is being spread, or it gives evidence to suggest that we should look at this pump and say, hey, why are people getting sick around this pump so much? Maybe there are germs there that we should look at. There's actually one little exception, which is that there's an abbey or a monastery nearby that pump where no one got sick, and that's because monks were there brewing their own beer and were therefore protected from the spread of cholera. 1913, Ford Harris came up with what is called the EOQ formula, the economic order quantity formula. It determines how much of a product you should buy if you're trying to satisfy the needs of your customers. Okay, so it's a formula that looks like this here. It has three variables. You have a setup cost of placing an order for a product. You have a rate of demand for that product, which we're calling D, and you have a holding cost for each unit of that product. And the EOQ formula says the optimal order quantity is this expression here, square root of 2KD on H. What the heck am I talking about here? Imagine that you've got a store and you sell things. Okay, now you have people who come into your store and they want to buy stuff. So you have a constant rate of demand. That's the letter D. Okay, D is how frequently people are coming into your store and asking to buy some product of yours. Now, you have to replenish your supply, right? You have to pick up the phone and call a supplier and say, hey, I need more shoes or whatever it is. And then they have to come to your store. The question is, should I be picking up my phone every day and placing orders? Or should I be waiting a long period of time in between placing orders? So what are the diametric sort of opposites that are happening here? Let's suppose every day I sell, 10 shoes, and then I pick up the phone every day and I order exactly 10 shoes to come in. Well, typically when you place an order, there's a fixed cost in place, right? For any order, regardless of the size, there's, a charge of $10 for a delivery fee or something like that. Well, if I'm ordering shoes every day to replenish my supply, then I'm going to rack up those fees pretty quickly. So that says, well, I shouldn't be ordering things all the time because there's this fixed cost in place, that's K, and I'd like to get around that. So what's the alternative? The alternative is make huge orders, but place them very infrequently, right? Place gigantic orders because I don't want to be picking up the phone a lot and making these phone calls and incurring these fees. What's the problem there? If I'm placing huge orders, I need to have a huge store to carry all this stuff. That's H. H is the holding cost for these products because it's the real estate cost that I have to pay in order to make sure that I have room to store all of my items. So those are the trade-offs there, K and H. Okay, K is how much it costs me every time I place an order. H is how much it costs me to have all this inventory sitting around in my showroom floor. And D is the rate at which people are asking for things. So this formula here, the EOQ formula, it tells me what the optimal size is for every order that I make. 1916, Lanchester's laws. Frederick Lanchester was a British mathematician who applied mathematical analysis to warfare. He looked at armies. He said, okay, if you have two armies competing with each other, how can you characterize their strength? He said, if you have hand-to-hand combat, okay, if people are using swords and axes and things like that, then one soldier can only attack one other soldier at a time. And so therefore, the strength of an army is proportional to the number of troops, right? If you double the size of the army, you double its strength because there's twice as many soldiers who can attack, therefore twice as many people. There's nothing really profound about that statement. The more deeper statement is that in modern warfare, you then have soldiers who can spread their firepower over the opposing army. And a consequence of that is, in fact, that the proportionality works as follows. The strength of the army is not proportional to the size of the army, but rather it is proportional to the size of the army squared. Now, where did that derivation come from? It's written over here. We're going to skip through it because it's not going to be on the exam. In fact, nothing that you've seen so far is going to be on the exam at all. I'm just trying to give some context here. Project Scoop was an Air Force project that took place in 1947. This fellow here at the right is George Danzig, who was my academic my academic grandfather. He was my thesis advisor's thesis advisor. Project Scoop, which stood for Scientific Computation of Optimal Programs, was a Pentagon-based U.S. Air Force research group that was formed in June of 1947. George Danzig was the lead mathematician for this, and he stated the general form of what is called a linear program, which is something you're going to know very well over the next few weeks. You have some variables here, x1 through xn. You have a linear function that you're trying to minimize, and you have linear constraints, in this case, that are all of inequality form, but they can actually be much more general than that. Danzig studied these problems and invented something called the simplex algorithm, which is still used today for solving these linear programs. And you're going to get to know the simplex algorithm very well. 1949 was when Ken Arrow's theorem became popular. So Ken Arrow was an economist who received a Nobel Prize in 1972, did work from 1949 to 1951 to try to model voting systems mathematically. Winston Churchill, I have a quote from him here. It said effectively that democracy is the worst form of government except for all the others. So Ken Arrow said, let's try and study voting systems from a mathematical perspective and try and say what works, what doesn't. Ken Arrow started off by saying, let's try and agree on some principles that any decent voting system should satisfy. Okay? Not to start off by looking for the best voting system. Maybe that would be an eventual goal. But he started off by saying, let's just try and agree on some basic principles here that any sane voting system really ought to obey. If you like, if you're watching this asynchronously, you could pause this now and think to yourself about what some of those rules should be. One voting system, it would be a bad one, would be to collect everyone's votes and throw them in the garbage, flip a coin, and pick a candidate. That would be a voting system. It would be a pretty terrible one. He said, I'm not going to look for the best voting system. I'm just going to write down some conditions that any rational person would agree should be satisfied by a good democracy. And so I've written them here. Pareto efficiency is the first one. If every voter prefers X over at Y, so every voter likes X more than Y, then the group should prefer X over Y. Okay, so if everyone in this class says, I want to have the final exam on Wednesday, then it would be a terrible voting system if I said, well, we're going to have the final exam on Monday, right? Any voting system in which that would be the outcome is a bad one. So that's rule number one, right? Axiom number one. Rule number two, independence of irrelevant alternatives. If every voter's preference between X and Y remains unchanged, then the group's preference between X and Y should remain unchanged. What do I mean by this? Imagine you go into a food court and you and your friend see that there's a hot dog stand to the left and there's a pizza joint to the right. And you'd say, which would you prefer? You ask your friend, would you like the hot dogs or the pizza? Your friend says, I'd like the hot dogs. And you say, oh, there's also a burger stand over there. Your friend says, oh, there's a burger stand. Oh, then I want the pizza. You'd say that friend is irrational. It makes no sense that whether the existence of a burger stand governs their preference of hot dogs over pizza. This is just extending that principle to a group, right? If all of the voters' preferences between X and Y does not change, then neither should the assessment from the group. You'll see an example of this to make this more clear, but I hope I've given you a rough idea of this. Non-dictatorship. No single voter possesses the power to always change the group's preference. Right? That's a no-brainer there. So those are three conditions. We're all just going to say that these are three basic properties that any good voting system really ought to satisfy. Right? These are weak conditions that we've established here. Let's look at some examples of voting systems that violate this. In fact, the way American voting works violates the independence of irrelevant alternatives. And I'll show an example of this to illustrate it. So we'll say that each person ranks the candidates from their most favorite, number 1, to the nth favorite. So there are n candidates. In a typical democracy, we give 1 point to the favorite and then no points to everyone else, right? Typically, you vote for your one favorite outcome, and then the rest of the choices just don't get acknowledged. It's not always the case. There are city governments that do things like approval voting or a lot of other options there whose names I can't remember, but we'll go with this one for now. So this actually violates this independence of irrelevant alternatives with this example here. Let's say we have 7 voters, and initially there's candidates A and candidate B. You can see in this example here that there are 4 voters, that like A the best, and 3 voters that like B the best. So we'd look at this first situation here, this first table, and we'd say, well, I think the group votes that A is the best option here because it's 4-3. Okay, now we'll say candidate C enters the race in this second table you see here. And so now all of those voters have their rankings. And you'll see that each of these same 7 voters, the preference between A and B does not change because the first 4 voters, as before, like A better than B, and then the last 3 voters prefer B to A. However, the first 4 voters, although they all prefer A to B, some of their preference of C relative to those other 2 varies. Right? You can see where C fits into the preferences over here. And the outcome here is we look at this and say, well, there are 3 people whose favorite outcome is B. That's 5, 6, and 7. But now there's 2 for A and 2 for C. So now what happens? Now B is the favorite because B has received 3 votes versus 2 for A versus C. Now notice here that no one changed their preference between A and B. Right? Those preferences stayed the same. But by placing C into the mix, suddenly B is the favorite instead of A. So this violates the independence of irrelevant alternatives as a result of this. It's a common criticism of how third parties get treated in the US. Right? The election in 2000 had an incident in Florida that many people think was caused by exactly this kind of situation. So you could say, well, all right, maybe we need to work on this idea about having each person get just 1 vote for their favorite. Let's try and do something. Here's something that is sometimes suggested. We'd say, okay, now we're actually going to not just have an emphasis on your favorite, but we're going to do the following. You have n candidates. Each person is going to rank those n candidates, and we'll say that the first choice gets n points. Points being some arbitrary mathematical quantity. The second favorite of each person gets n-1 points, and so on and so forth. This is just a scheme I've invented out of nowhere just to give another example of a violation of the independence of irrelevant alternatives. Here's an example where you've got 5 voters and either 3 or 4 candidates. And under this system now, it turns out that B would get 11 points, A would get 10 points, and C would get 9. And then when candidate D enters the race, all of a sudden A becomes the favorite with 15 points versus 14 for B, and so on and so forth. So again, we're violating the independence of irrelevant alternatives. So that's 2 examples that I've given. In fact, this theorem by Ken-Arrow isn't just called Arrow's theorem, it's called Arrow's impossibility theorem. Because in fact, Ken-Arrow proved that there's no such voting system that exists that satisfies these 3 conditions. He said you can't do that. There is no ranking-based voting system that satisfies those 3 conditions. It doesn't mean that voting is hopeless. It means that there's no system in place for obeying these conditions that is just based on ranking, by which I mean the ordering of the candidates from your favorite to your least favorite. Approval voting, in fact, does satisfy these conditions. Approval voting means that rather than having any kind of ranking, you simply go through all the choices and you check off the choices that are agreeable to you. You can check off all of them, you could check off none of them, you could check off half of them. And then in the end, the winner is the person who receives the most checks. That, in fact, satisfies all of these conditions. And Stephen Brams at New York University's Department of Politics has written several books on why this is he believes this to be a powerful system. Game theory and the prisoner's dilemma. Game theory is a method of studying strategic situations. Strategic means that you have multiple parties that are in play and they're competing against one another and they're all trying to optimize their own welfare, possibly at the expense of the other parties. The best example of this is the prisoner's dilemma, but rather than give you my take on it, I'm just going to put a link to the video above, which explains it much better than I could hope to do. In 1955, Lighthill and Witham proposed a model of traffic flow that looked at vehicle traffic as being a fluid that moves throughout a pipe. They said, well, trucks and cars move on the road in a way that is a lot like the way water flows through a pipe. So maybe the mathematical models that we already use to model the flow of water in a pipe could be applicable here. They said you have flow conservation, which means that cars don't appear out of nowhere. They don't vanish either. And there's also a functional relationship between the traffic flow and the density. The more traffic you have, the denser things are, right? The slower things move. So they said that traffic flow at a point x and at time t will be called this function q, and you have a functional relationship seen in this equation there, which you don't need to remember. It's not on the exam. I'm just including it for decorative purposes. They have the partial differential equation you see here that says that nothing appears or vanishes. This is called flow conservation if you've ever had a course on PDEs. If we assume that the flow is just a function of density, then we get the nonlinear wave equation, which you see here, which also appears in physical mechanics all over the place. One thing that this is notable for is that it accurately predicts the appearance of shock waves, in other words, traffic jams. This kind of science was pretty popular throughout the 1950s. Some scientists at General Motors proposed a car following model that took into account the individual drivers in the vehicles as well. Let's talk about the stages of mathematical modeling when you are trying to solve a problem. I like to think of the stages of solving a problem as having 5 parts to it. There's the recognition of the problem, there's the building the model and data collection, there's the solving the model, there's validating the model, and then there's implementing it. So what do I mean by all these things? Problem recognition is step 1. What are you trying to do? Are you trying to minimize your costs? Are you trying to maximize your profits? Are you just trying to solve for some variables that make people happy? You have to identify what is under your control. You have to identify what you can't control. And you want to identify what the givens are to you. What are the rules that are thrown at you that you don't have under your control and that are taken as input parameters to your model? You'd be surprised at how difficult this problem actually is when you get into the real world. You encounter companies that don't actually know what their goal is. They might need your help in figuring that out. They might identify a number of criteria that they want to simultaneously satisfy, but they don't know which one they should be seeking to optimize the most. Should they be improving their quality? Should they be improving their customer retention? Should they be improving their flow of revenue? All of these things could be decisions that are important to them, and it's not always as clear as it might seem what the right answer is. We're going to look at a simple example here to illustrate this point. You've got a company that makes a product, and the demand for that product varies, as it typically does, as a function of the price of the product, right? You charge a high price for the product, fewer people want to purchase it. The company, of course, wants to make as much profit as possible. They want to maximize the revenue minus the costs. The company can control the price of the product. Given a particular price, the demand for the product is determined by some function. I can't control the demand of the product, right? Me, the company, I can't control the demand. I can control the price, and that has an impact on it. We'll also say that it costs the company $5 to produce 1 unit of the product. That'll be the problem recognition. We say we're going to maximize our profit, and we've identified these various costs and so forth that go into things. So let's do the model building. When you build a mathematical model for this kind of problem, you'd want to decide what are your decision variables versus your parameters. Again, the variables represent things that are under your control. In this example, the only thing under your control is the price. Parameters are things like the $5. The $5 that you have to pay per item that you build. The $5 is not under your control. That is a parameter. That's an important distinction that you're going to be very familiar with by the end of this course. Then you have an objective, also called a goal or a target. The objective is the thing that you're trying to maximize or minimize. It's the expression that you want to make really big or really small. In this case, our goal is to maximize our profits. We'd say that's our objective. What are constraints? Constraints are conditions that are imposed on you externally. Right? The constraint would be that you can't manufacture more than a certain number of items because you don't have enough labor on hand or something like that. It's a constraint that's imposed on you, or a condition, a limitation, a requirement, some sort of imposition that you have to deal with. You say a constraint is either satisfied or it's violated. Right? Typically, your constraints all have to be satisfied in order for the problem to make any sense. So in this example here, we would model, let's say, the relationship between the price and the quantity of demand as this expression here. Q is equal to 10,000 minus 100 times P. Where did that expression come from? Well, that would have come from something internal to the company, where a data analyst would have performed some kind of linear regression or something and worked out that that was the relationship. So Q, the quantity of demand, is equal to 10,000 minus 100 times P, where P is the price. So this has some intuitive niceness to it because, of course, as the price increases, Q decreases, which is exactly what we expect to happen. It's kind of weird that in this case here, if P is greater than 100, then Q would be negative. And that doesn't really mean anything. Negative demand for a product, I'm not sure that has a well understood interpretation. So there should probably be some caveat here that this expression only makes sense for values of P less than 100. But we'll assume this equation holds true, and the company is going to try to choose the optimal price to maximize their profit subject to this constraint. So this equation here about Q is a constraint. It relates Q, the quantity of demand, and the price. The production cost of $5 per unit is a parameter, and the total profit that the company makes is the revenue minus the expenses. That's given by this formula over here. The revenue is P times Q, because it's the price that you're selling times the quantity of demand, and then minus 5 times Q, because $5 is the cost you pay per unit, and then Q is the quantity of demand. And then if you plug in that constraint that I wrote up there, that Q is equal to 10,000 minus 100 times P, you'd get this expression here on the right. It's 5 times the quantity, 10,000 minus 100 times P. Our objective function is to find the value of this variable P that makes this as large as possible. We want our profit to be as big as we can possibly get it to be. Model solution. So now we've reduced things to finding the value of P that maximizes this expression. So we solve that. Typically, you'd do this with a computer. You use the simplex method, which we'll learn in this course. You'd use branch and bound, which you'll use in this course. You'd use dynamic programming, which is something you'll learn in this course. You'd use technology to solve these problems. In this case here, the problem's pretty simple. We know how to solve it because we've all taken single variable calculus. We say a solution is feasible if it satisfies all of our constraints. Otherwise, a solution is infeasible, meaning you can't solve your problem because the constraints are preventing you from meeting all your criteria. We say a solution is optimal when it's the optimal solution, when it's the actual solution to the problem. So this problem here has just one variable. You're trying to maximize this expression here of P. And so what do we do with that? We take the derivative of that expression and we set it equal to 0. In fact, most of optimization is really just setting derivatives to 0 in a really advanced, complicated kind of way. You might remember the method of Lagrange multipliers from multivariable calculus. You've probably forgotten it, which is fine. In operations research, we call the method of Lagrange multipliers the KKT conditions, and they generalize to a much broader family of problems. We'll get to that later. For now, all we're going to worry about is taking this expression here, the expression for profit, and maximizing it by setting the derivative to 0. We differentiate this thing, set the derivative to 0, and solve for P, and we get an optimal value of P equal to $52.50. I've written a little star next to P there. That's what we typically do when we're writing the optimal solution to a problem. When I'm indicating that I've solved something, I put a little star next to it like that, P star, which is $52.50 in this case. And we go back to our customer, we say, hey, this is the price that you should charge. You should charge $52.50 for every unit of the product. That will maximize your profit. The profit that you get is going to be equal to this value here. You plug in P star to this expression, and you get $225,625 in profit. That's what you report to your customer, and you say that you've solved the model. The next step is model validation. You have to check if the model actually makes sense in the real world. If it doesn't, then you have to revisit the model. I can't tell you how many times in my own practice I've had a customer or a client who needed help with something, and I thought I had solved the problem and I brought it back, and then they said, oh no, this doesn't make any sense because of a bunch of other conditions that I forgot to tell you about. It happens so often that it deserves its own entry here, which is why I've marked it there. In this case, I've introduced a very simple complication, which is that you take this to an analyst, or the specialist rather, and the specialist says that this price is too high because the analyst forgot to factor in a fixed cost of $50,000. So we have to subtract $50,000 from this total profit that we've optimized here. So we subtract that and then get a new value there. I said 50,000, I should have said 30. I wasn't looking carefully enough at my slides. So once we've done that, we've validated the model, it makes sense. The last stage is implementation. You take that model and you say, how am I going to actually do this in the real world, right? So we've already made a recommendation for the price. We've said the price that you should charge is $52.50 per unit. And let's say currently the price is $46.99 per unit. And the company says, I don't want to jump my prices up this big all at once because I'll get whatever nasty tweets, my customers will be upset, they're going to be worried that the company's going out of business, I'll lose my social capital, you name it, right? There's a whole set of things that might go wrong with that. So the company might say, what we're going to do is we're going to steadily increase this price over the course of several months, several weeks, whatever the time period might be. That's the 5-step process for mathematical modeling that we're going to abide by as we go through this course.